Good morning. This is your Stats Sensei, Mr. Spensei, and this is Death Packet Unit 3A, Classical Probability. And this will be problems 71 through 80. So given two events, E and F, such that E is 0.34 and F is the probability of F is 0.45, and the probability of E union F equals 0.637, when the two events are, and they want to know if they're independent and mutually exclusive. Well, I need to start off by writing down my equation. So the probability of E union F equals the probability of E plus the probability of F minus the probability of E and F. All right, so we have that, and we find out that E union F is 0.637. The probability of E is 0.340. Probability of F is 0.45, and the intersection we don't know. So I'm going to use the intersection symbol. So let's add those two up. So when we add up 0.340 and 0.450, 0.34 plus 0.45 is 0.79. So 0.637 equals 0.79 minus the intersection. Subtract 0.79 from both sides, and I have 0.637 minus the 0.79, and I end up with negative 0.153 equals a negative n. So changing both signs, 0.153 equals n. Well, the fact that that we have an intersection means that it's not mutually exclusive. So mutually exclusive is gone, any of the ones that say mutually exclusive. All right. The question is it independent? Well, if it's independent, we have to remember that the probability of E times the probability of F equals the probability of E and F. Well, in this case, the probability of E is 0.340, and the probability of F is 0.45. And we just said that it has to equal, their intersection was 0.153. So let's see if that's true. If it's true, they're independent. So 0.34 times 0.53, and we end up um, 0.34. Oops, I typed in the wrong numbers. 0.34 times 0.45 is 0.153. So 0.153 equals 0.153. Because this times this equals the intersection, they are independent. So our answer choice is B. They're independent, but they're not mutually exclusive. And remember, they don't have to be either one. So following are the parts of a probability distribution for the random variables X and Y. Okay. So interesting things about probability distributions. All the probabilities have to be less than one, or one or less, between 0 and 1, and they have to sum up to a total of 1. And we're going to need that information. So it says X and Y are independent. Well, that means I can multiply them if that comes up. And the joint probability of X comma Y, that really means, that's another way of saying X and Y equals 0.12. So X times Y, when X is 1 and Y is 2, is 0.12. So it says, what's the probability of X equals 4? Well, I go to X is 1. Okay, this means I need this one, and Y is 2. So I need this one. And I need those two, but I don't have either one of them. So I can't go this times this and do any more work. But I know this is a valid probability distribution. So, and I add those up, and 0.43, 0.4 plus this value Y that we don't know, or Y2, plus 0.3 has to equal 1. Well, I add these two up and I get 0.7 plus this y value equals 1. Subtract 0.7 from both sides. Now I know that y equals 0.3. So this value right here is 0.3. Well, that's interesting because now I have a little more information because I was interested in 1 and 2, and now I have 2. So remember, the probability of x times the probability of y equals the probability of x and y if they're independent. Well, we know this is 0.12. We know this is 0.3, and we just don't know x. Well, if I divide both sides by 0.3, I should be able to get x. Should put an equal sign there. And 0.12 divided by 0.3 is going to be 0.4. So this value, x equals 0.4, and we're all excited that we have this, but they wanted this, so I need to figure this out. Well, remember, the sum of all these values has to equal 1. So coming back to that, we have 0.4 plus 0.2 plus 0.3 plus x has to equal 1. So I add these up. This is 0.6, this is 0.9. So 0.9 plus x equals 1. I subtract 0.9 from both sides. And I end up with x equals 0.1. So my answer choice is A. All right? That's a long one. Actually, this whole video will be a long one. All right, number 73. Suppose x equals 0.25 and y equals 0.4. If the probability of x given y equals 0.2, what's the probability of y given x? Well, let's set up our formula. So our formula is the probability of x given y equals the probability of x and y over the probability of y. So when I plug in to this, I'm going to have, okay, this is 0.20. X and y, we don't know. I'm just going to use the intersection symbol. And the probability of y happens to be 0.40. Okay. Is that correct? Yes. So I need to multiply. I need to get rid of this. So I need to multiply both sides by 0.40. This will cross out. And if I go 0.4 times 0.2, I end up getting 0.08. So my intersection equals 0.08. So that's the probability of x and y. All right. So the other side, they go, well, what's the probability of y given x? Well, the probability of y given x, that's the formula, equals the probability of x and y over the probability of x. Well, we just found out that the intersection is 0.08. So that's going to go right here. So that's 0.08. And we know x happens to be 0.25. So 0.08 divided by 0.25 equals 0.32. So the probability of y given x equals 0.32. All right. So our answer choice on 73 happens to be C. Okay, moving on. The following is from a particular region's mortality table. What's the probability 20-year-old will survive to be 60? Well, what they're saying is, oh, we started off with 10,000 people. Then at age 20, there were 9,700 left. At age 40, they're 9,240. At 60, 7,800. And 80, there's 4,300 left. So this is a case of given. All right. So given that they live to 20, and it's intersection over given, well, 9,700 live to 20. Of that, 7,800 live to be 60. So 7,800 divided by 9,700 equals 0.8041. So my answer choice to 74 is B. A computer manufacturer sets up 3 locations to provide technical support for its customers. Logs are kept noting whether or not calls about problems are solved successfully. Data from a sample of 1,000 calls are summarized in the table below. Okay. Assuming there's no association. Now that's a key phrase. No association means they're independent. All right. And if they're independent, then we can say, oh, the probability of A and B equals the probability of A times the probability of B. Between location and whether or not a problem is resolved. What is the expected number of successful calls? So problem solved from location 1. All right. So they're saying there's no association. So we want to use this formula. They're saying they're independent and they're problem solved. Well, first off, the probability they came from that is 700 over 1,000. And location 1. And that probability is 450 over 1,000. Now, I'm going to leave it just like this for a moment. And so that's the probability. It says, what is the expected number? Oh, well, expected number has this formula. Expected number equals N times P. Well, what's N? Well, N is 1,000. So I need to take my probability, which is this. I should write this below this a little nicer. The expected value equals N times P. Well, N is 1,000 times my probability of 700 over 1,000 times 450 over 1,000. And I go, oh, well, those cancel out. So I'm left with 700 times 450 over 1,000. So I should be looking for, so I should be looking for that answer. 700. Well, this is 325, so that's not right. This is 325, so that's not right. This is 325, that's not right. 325. Oh, here we go. 450 times 700. 450 times 700 over 1,000. So my answer choice to 75 is E. All right. A plumbing contractor obtained 60% of her boiler circuits from a company who has a defect rate of 0.005, and the rest from a company whose defect rate is 0.001. If a circulator is defective, what's the probability that it came from the first company? So a lot of times that if I have 3 probabilities, which I have here, it's oftentimes going to be a table. And this one is going to be a one I have to solve using a table. So I need to identify the number that's associated with one variable. 60% obtain 60% of a boiler from a company. That has nothing to do with defect rate. It only has to do with one variable. All right. So let's set this up. So let's set this up and see if this works out. I hope it does. All right. So I'm going to have to give myself a little more room. So I'm going to write this on a separate sheet of paper. So 60% from a defect rate of, and this is at the bottom of the page, which makes it difficult. That's being a little better. So I'm drawing my little window. That's not a very good window. So 60% from this one, and that's from company one. From company two, I'm getting 40%, and that's one whole. And defect, not defective. Those are my two variables. Well, I'm going to write the 60% really small. So this is 0.6. And this is 0.6. This is 0.40. And this is 0.40. Defect rate is 0.005. So company one and defect 0.005, 0.005. Then I'm going to go 1 minus that, which is 0.995. That's a probability it's not defective. And let's go ahead and multiply those out. 0.6 times 0.005 is 0.003. And 0.6 times 0.995 is 0.597. Okay, so those sum up. Because this plus this needs to equal this. And then they say this one has a defect rate of 0.01. Well, this is 0.01. Well, 1 minus that is 0.99. 1 minus 0.01, 0.99. All right. So I need to multiply those. So 0.4 times 0.99 gives me 0.396. And 0.4 times 0.01 is 0.004. I add these two values up because this plus this equals 0.007. And this plus this equals, better be 0.993. So 0.597 plus 0.396, 0.993. And I just checked, and this plus this equals that. So my table looks like I made it right. So as if a circulator is defective, what's the probability it came from the first company? Well, that means given that it's defective, all right, well, the defect rate is 0.007. And remember, it's always intersection over given. Well, another word for given is if. Well, they tell me that this is 0.007. So that's this. And from company one, that's 0.003. So there's my fraction. Let's test it out. So 0.003 divided by 0.007, and we end up getting 0.4285. 0.4285. The answer that's closest is 0.429. So my answer choice to 76 is A. Moving along. Another table. The probability a person will show a certain gene transmitter trait is 0.8 if the father shows a trait and 0.6 if the father doesn't show the trait. Suppose the children in a certain region, certain community come from families and 25% of which the father shows a trait. Given that a child shows a trait, what's the probability that her father shows the trait? So first off, we have three numbers. So that kind of tells me I'm looking for a table. Hope I have enough room for this. All right. So here are my three numbers. The probability a person will show a trait is 0.0 if. That's conditioned. So this is on two numbers. And 0.6 if the father doesn't. Ooh, so this is also two. So I hope this next one has only one. Suppose children in a certain community come from families, and 25% father shows the trait. Okay, so 25% have the trait. So this sounds like that's one. So this is one whole. 1 minus 0.25 is 0.75. This has the father has the trait. Father does not have the trait. All right. So gene is transmitted to the child in 0.8 if the father shows a trait. Let me go ahead and write these up small. So this is 0.25, 0.25, and this is going to be 0.75 and 0.75. So gene transmitted, gene not transmitted, and 0.8 if the father shows the trait. Father shows the trait, genes transmitted. This is 0.8. 1 minus 0.8 is 0.2. Let's multiply that out. 0.25 times 0.8 is 0.2. And then 0.25 times 0.2 should be 0.05, and it is, because these need to add up. This plus this needs to equal this. And then it says, and 0.06 if the father does not show the trait. Father not show the trait, but there's a 6% chance. So this is 0.06. This is 1 minus that, which is 0.94. So 0.75 times 0.06 is 0.045. And this is 0.75 times 0.94 is 0.705. It looks like these add up. This plus this equals 0.755. Let's check that out real quickly. 0.705 plus 0.05, 0.755. And then we have 0.2 plus 0.045, which is 0.245. And this plus this equals 1. So given the child shows a trait, so given the gene was transmitted, so remember it's always intersection over given. Well, the given they show the trait is 0.245. What's the probability the father shows the trait? So we're looking for this and this. Well, that intersection is 0.20. So 0.2 divided by 0.245 is 0.816. So my answer choice to 77 is D. 78, given a probability of 0.65 that interest rates will jump this year and a probability of 0.72 that if interest rates jump, the stock market will decline. What is the probability the interest rates will jump and the stock market decline? All right. So this is a little bit difficult to read, but given that interest rates will jump and a probability of 0.72 that if interest rates jump the stock market. So if they jump, this is telling me that given that the interest rate jumps, this is the probability stock market decline. So this is the probability of A given B equals the probability of A and B over the probability of B. So given this probability, so this is my B happens to be 0.65. And this one's hard to read, so I'm going to jump down just a bit. So this is 0.65. What's the probability interest rates will jump? And that's my intersection. So I'm looking for my intersection. And what I was given was that if this happened, then this would happen. And that if tells me that this is the probability of A given B. So this is 0.72. Oh, okay. Well, to solve this, I need to come back and multiply both sides by 0.65. This goes away, and I find out that my intersection equals 0.65 times 0.72. That's not this. Oh, there it is. All right, so the answer choice to number 78 is B. Suppose 4% of the population have a disease. A laboratory blood test gives a positive reading for 95% of the people who have the disease and a 5% for those who do not have the disease. If a person tests positive, what's the probability that the person has the disease? So, once again, we have three numbers. 4% have the disease. Oh, that's one variable. That makes it nice. It happened to be the very first one. So we found what we needed. We can go ahead and make our table. So 0.04. This number is always 1. 1 minus 0.04 happens to be 0.96. I can write these small. 0.04, 0.04, 0.96, 0.96. We just bring those up. This is the probability of a disease. This is not disease. And what was the other variable? Positive. Oh, so we're giving test results. So my other is test results, which is positive and negative. A laboratory gives a positive reading for 95% of those who have the disease. So this is 0.95. 1 minus 0.95 is 0.05. And 5% of the people who have the disease. So it gives a positive result for 5% who don't have the disease. So that means 1 minus 0.05 is 0.95. So we can go ahead and start multiplying all this out. So 0.04 times 0.95 is 0.038. .04 times 0.05 is 0.002, and that's good because this plus this needs to equal that, and it does. 0.96 times 0.05 is 0.048, and then 0.96 times 0.95 is 0.912, and this plus this equals that. Now I need to add crosswise. So 0.038 plus 0.048 is 0.086. And 0.002 plus 0.912 is 0.914. So if a person tests positive, so intersection over given, well, what were we given? That they tested positive. What's the probability of positive? That's 0.086. What's the probability the person has the disease? And I see that's 0.038. So in this case, 0.038 divided by 0.086 is 0.4418. And the answer choice that's closest to that is C. All right, the Air Force received 40% of its parachutes from Company C and the rest from Company C2. All right, the probability that a parachute will fail to open is 0.0025 or 0.002, depending on whether it came from C1 or C2, respectively. That means 0.0025 came from C1. This is from C1. This one came from C2. If a randomly chosen parachute fails to open, what's the probability that it comes from C1? Once again, we have three numbers. This is probably going to be a table, so let's go ahead and start making one up. Draw my window. That's a bad window again. All right. 40% of the parachutes come from C1. Oh, well, that's not conditioned. That's only on one variable. So I'm going to call this company C1. This is company C2. This is 0.40. This is 1, always 1. 1 minus 0.4 gives me the 0.60. All right. The probability parachute fails to open. Oh, this is fails, not fail. And we're going to bring up our numbers. 0.40, 0.40, 0.60, 0.60. The probability parachute will open is 0.0025 for the first company, 0.0025, and 1 minus 0.0025 is 0.9975. So 0.4 times 0.0025 is 0.001. And 0.4 times 0.9975 is 0.399. That's good because I need these two to add up to 0.4. The next one, this is 0.02. That means this is 1 minus that, which is 0.998. So 0.6 times 0.002 is 0.0012. And 0.6 times 0.998 is 0.5988. If I add up these two numbers, this plus this, 0.001 plus 0.001. Oops, I hit a minus sign. That's not going to work. 0.001 plus 0.0012 is 0.0022. And 0.399 plus 0.5988 is 0.9978. The sum of these do equal 1, so that looks good. So if a randomly fails to open, so if is a given word, so intersection over given, or in this case, intersection over if. And we're looking at this is what we're given, so this is 0.0022. What's the probability came from company 1? Oh, there's my intersection, 0.001. So 0.001 divided by 0.0022, and I end up getting 4545. Answer choice is D. All right. Appreciate you watching. Hope to see you on the next one. Thank you.